previous classes, we have seen the relations and correlations for external flow as well as for internal flow. In all these cases, there was an imposed pressure gradient, especially for internal flow, which drives the fluid through the tube. But there are several occasions in which there is no externally imposed flow on the system, even though a flow will automatically start because of a difference in buoyancy. So, this buoyancy difference driven flow will lead to convection as well, which is known as the free convection or natural convection. This is a very important part of the overall transport process. Around many structures, buildings, surfaces and occasions we would come across natural convection. So, wherever there is an absence of a forcing velocity, the heat transfer under that situation, which is caused by density difference due to temperature, is termed as free convection or natural convection. So, they are characterized by the absence of any velocity, any imposed velocity on the system. The applications of natural convection, as I mentioned, are many. They appear in atmospheric process to semiconductor chips. When a semiconductor chip is cooled in absence of a fan which forces the fluid to move over it, the way it loses heat is natural convection. So, from a very small length scale to a very large length scale, we will have natural convective heat transfer under many situations. So, it is important to know what are the what's the physics of natural convection, what are the relations and correlations which are to be used in order to obtain the heat flux or the heat transfer coefficient in natural convection. And just to have an idea of what kind of a heat transfer coefficient, the order of magnitude value of the heat transfer coefficient that one would encounter in natural convection process. So, let us look at the development of the governing equation and see what additional information we can obtain by simply doing writing the equation of energy, equation of motion and equation of continuity, and see what would be the similarity parameter or which dimensionless group would automatically appear in those equations. So, any relation of heat transfer coefficient will therefore be a function of, for example, Nusselt number would be a function of, besides Reynolds and Prandtl, some other number which may appear for the case of natural convection. And the point to start this analysis is the fundamental equations, the energy, the motion and the continuity equation. So, let us look at the figure over here, which shows that I have a plate which is in contact with air. The plate temperature is Ts and the temperature of air, surrounding air at a point far from the plate is T infinity, and the corresponding density of air is rho infinity. The gravity is acting this way, and we will assume that the temperature of the plate is more than the temperature of the air. So, therefore, the fluid near the wall, its temperature will increase, its density will decrease and it would start to rise up. As it rises up, this fluid is going to be replaced by cooler fluid from here. So, you have a cooler fluid from over here, and then the process would start once again. So, the hot fluid near the wall rises towards the top to be replaced by cold fluid from the ambient. So, this is what is known as free convection, and free convection are also classified based on according to whether the flow is bounded by a surface, and free boundary flows may occur in the form of a plume or a buoyant jet. Okay, so, let us write the equation. Let us assume that the flow inside, the density difference imposed flow inside the boundary layer is laminar, but however, it is also possible that we will have turbulence at some point at a larger value of x. So, this is x equal to 0, y equal to 0, that is the origin that we have, and the velocity in the x direction is u, the velocity in the y direction is v. And we understand that the flow outside of this thin layer is essentially stationary. So, both u and v will be 0 at this point from this point onwards. So, if I that's why if I draw the velocity profile of the air which is rising close to the plate, it is going to due to no slip, the velocity would be 0 here, and as we understand the problem, the velocity will also be 0 over here. So, in between it will follow some sort of a profile where the maximum would lie at some point in between, but the velocities are going to be 0. The x component velocities are going to be 0 here and as well as here, and we understand that v is going to be very small. The velocity in this direction is going to be very small as compared to the velocity in the x direction. So, the x momentum equation, is simply going to be u del u del x plus v del u del y minus 1 by rho del p del x minus g, since it is acting in the minus y direction, plus nu del square u by del y square. Note that I have neglected the viscous transport of momentum in the x direction, as the velocity gradient in the x direction is very small as compared to the velocity gradient in the y direction, due to the thinness of the region where this flow is taking place. However, u is large as compared to v, but del u by del y is very large as compared to del u del x. So, none of the terms, the simple boundary layer approximations, none of the terms on the left hand side could be neglected. However, we also know that if I write the y component of the equation of motion, since there is no force in the y direction, the gravity is acting downwards. So, del p by del y would be 0. This is from the y momentum equation. So, y momentum equation would give you del p by del y would be equal to 0. So, pressure gradient at any point inside the boundary layer must be equal to the pressure gradient in the region outside the boundary layer. So, the pressure gradient at these 2 points would be identical, since del p del y is equal to 0 and p does not vary in the y direction. So, if that's the case, then the y momentum equation, and in this region u is 0, there is no velocity in the x direction, no velocity in the y direction. The effect of gravity from the the gravity would be there, but the velocity variation with y is also not going to be present. So, this equation, the equation that I have written over here, the x component of the momentum equation, if I write it for a region outside of the thermal boundary layer or outside of this layer, then all these terms would be 0 except minus 1 by rho del p del x and minus g equal to 0. So, that is the form of the equation if I write it outside of the layer. So, when you do that, we also understand that so therefore, del p del x would be equal to minus rho times g, and the rho refers to the rho over here. So, therefore, the rho is essentially rho at infinity. So, this is what we would get for the pressure gradient in the x direction. So, therefore, del p del x would be equal to minus rho infinity times g. So, it is straightforward. Now, I am going to put this back in here. Okay. So, if I put this equation back in here, then the left hand side will remain the same. The right hand side, these two terms can therefore be clubbed together to give the equation as del u del x plus v times del u del y equals g by rho infinity minus rho plus kinematic viscosity del square u by del y square. Now, this is the term therefore, which is the force, body force, which is acting on the fluid at under natural condition. To express this in a more convenient form, we introduce a thermodynamic quantity which is the volumetric thermal expansion coefficient. The volumetric thermal expansion coefficient, which is termed as beta, and you know that beta is nothing but minus 1 by rho del rho by del T at P at a constant pressure. So, for beta can also be approximated as minus 1 by rho, the change in density. So, rho infinity minus rho by change in temperature, which is T infinity minus T. So, therefore, this rho infinity minus rho can be written as beta rho T minus T infinity, absorbing the minus sign in here. Therefore, this equation can be written as u del x plus v del u del y as g beta T minus T infinity plus nu del square u by del y square. So, this is the equation of motion where we have introduced a thermodynamic parameter beta, which is known for most of the gases, and therefore, if we know it is better to express it is in terms of the delta T rather than in terms of delta rho by introducing the concept of volumetric thermal expansion coefficient. And the equation of continuity and energy, those are the two remaining equations, which can be written as del u by del x plus del v by del y equal to 0, which is equation of continuity, and equation of motion is this. This is the thermal diffusivity. So, these three equations are to be solved simultaneously in order to obtain what is known as the coefficients for the thermal coefficients for the relations for natural convection. One point I would like to make here is that the next step involves non-dimensionalizing the equation as we have done before, and in order to non-dimensionalize this, we need to express this in terms of, we first have to define a length scale, which is straightforward, because the length scale would most likely to be the length of the plate along which this rise of the liquid is taking place. It is to be also non-dimensional. I have to also bring in, since we have velocity, I also have to bring in some reference velocity, which is yet to be decided what that reference velocity would be. So, when you non-dimensionalize everything, I am simply going to write the dimensionless form of the equation without going through all the steps. What I would suggest to you is that look at Incropera and DeWitt, the textbook of this course, for the derivation from the dimensional equation to the dimensionless equation. But those steps are merely substituting the variables in terms of the dimensionless variables, and no new physical concepts are involved. So, I will skip those steps and only write the dimensionless form of the equation, which would give us more insight into the natural convection process. So, I will directly proceed to writing the dimensionless form of the equation and see what other information we would get out of this. So, the dimensionless form of the equation therefore is written as u star, which is the dimensionless velocity del u by del x, dimensionless distance, the dimensionless v y also equal to g beta T s minus T infinity times L. This is the length scale that I was talking about. U naught square is the velocity, reference velocity, yet to be determined reference velocity. T star is the dimensionless temperature plus 1 by R E L del square u star by del y star square. Just see this equation and compare this equation mentally what would have obtained if this is if this is a case where there is no temperature gradient present in the system. So, if there is no pressure gradient present, no temperature gradient present in the system, then this equation of motion would simply revert to the equation that we already know. The first term on the right hand side would be 0, since T s would be equal to T infinity. So, these two terms will remain and this term will remain as well, and you can clearly see that the similarity parameter for such a case, as we have seen countless times before, would be the Reynolds number. So, for a situation in which there is no temperature gradient, no temperature difference, natural convection does not take place, and the equation of motion will have the known similarity parameter as Reynolds number only. However, in presence of a temperature difference between the plate and the surrounding air, I have an additional extra term as the first term on the right hand side of the momentum equation. So, anything that I define will not only contain the similarity parameter Reynolds number, but it should also contain something which will consist of contribution from the first term. And again, the contribution from the first term is nothing but the contribution from natural convection. So, let us work a little bit on that term to see if any additional dimensionless terms come out of the first term on the right hand side. But in order to do that, if you look at your class note once again, you have an u0 square present in that term. u0 is a velocity, is a reference velocity that we haven't decided what it is. So, we need to get rid of this u0 square in some way. So, let us work on that, and what I would do is I would multiply both sides by REL square, where it is the Reynolds number based on the entire length, which would be u0 L by nu whole square. So, if you to remove the unknown reference velocity, this term is multiplied by Reynolds number square, and what you would get is a new dimensionless number which is known as Grashof number, which is denoted by GR based on the length as G beta T s minus T infinity times L by u naught square into u naught by L nu, which is Reynolds number square. So, G R L would be G beta T s minus T infinity L cube by nu square. So, this is the Grashof number, and the Grashof number has the same significance as Reynolds number in forced convection. So, similar to Reynolds number in forced convection. So, the same role the Reynolds number played in forced convection. So, that we know that for forced convection the Nusselt number is a function of Reynolds number and Prandtl number. So, whatever role Reynolds number played in the case of forced convection, the same role will be played by this Grashof number in the case of natural convection or free convection. So, the value of the Grashof number, can simply be expressed as the force, as the flow due to natural convection, and the flow due and it's a ratio of two forces, the viscous forces in the denominator and the temperature induced forces in the numerator. So, any relation that you would get for natural convection should therefore contain the Nusselt number for natural convection should be a function of Reynolds number, a function of Prandtl number, and a function of Grashof number. So, unlike forced convection, we will have an additional term present in any relation or correlation of natural convection, which is Grashof number. So, let us look at Grashof number in a bit more detail. So, therefore, what I say is that the Nusselt number is therefore based on the length is therefore a function of Reynolds number on the length, Grashof number based on the entire length and Prandtl number. So, this is what we should expect for any relation in natural convection. Additionally, this Grashof number, if you look at the definition of Grashof number, it is nothing but the ratio of buoyancy forces to the viscous force. Okay. So, I will write the definition of Grashof number once again, G beta T s minus T infinity L cube by nu square. So, this refers to the viscous force and the numerator refers to the buoyancy force. So, if Grashof number based on the entire length by R E L square is about 1, so combined effects are to be taken. So, combined effects of free and forced convection, this both will have to be taken. If your Grashof number by R E L square is very much less than 1, then free convection can be neglected. This you can clearly see from the definition of this. So, if your this value is very less than 1, then the buoyancy force, therefore, free convection can be neglected. And if on the other hand, if Grashof number by R E L square is way large as compared to 1, then the forced convection effects can be neglected. Okay. And if forced convection effect can be neglected, for that special case when forced convection effects are neglected, for that case NUL would simply be a function of Grashof number based on length times Prandtl number. So, if both are present, then the functional form is going to be Reynolds, Grashof and Prandtl. Now, if you have only if you have this to be less than 1, then the free convection effect can be neglected, and therefore, the equation would simply be Nusselt number is as a function of Reynolds number and Prandtl number. And if on the other hand, the Grashof number by Reynolds number square is way larger as compared to 1, then the forced convection effects can be neglected, and your Nusselt number is simply going to be a function of Grashof number and function of Prandtl number. So, a large number of relations and correlations are available for free convections. So, what I am going to do is I will simply give you some examples of those relations. For example, Nusselt number, average value of Nusselt number in natural convection as H L by K. This H bar is the average heat transfer coefficient for free convection, which is given as 4/3 Grashof number based on the length by 4 to the power 1/4 times G P R. This G P R is a function of Prandtl number, the values of which are provided in the text. These correlations are quite complicated, and of course, I do not want you to memorize, and it is not also possible to keep everything to remember all these relations or correlations, but you should know when to use which relation. So, in any questions in any exam, I am going to provide all these relations to you. You have to pick the right relation or correlation citing justification and then use it to solve the problems. So, the expression for Nusselt number which I have written in my slide is it's a function of Grashof number, and as I said, it has to be a function of Prandtl number. The function of Prandtl number, the functional dependence on Prandtl number is provided by the function GPR. So, the expression for which is there in your text, and you can simply use that in order to obtain what is the value of the heat transfer coefficient for natural convection under laminar flow. I am going to give you some more examples of these relations. So, some other relations for forced convection, I mean free convections are Nusselt number x as 0.508, Reynolds number, sorry, this is Rayleigh number to the power 1/4 and Prandtl by 0.952 plus Prandtl to the power 1/4. This is a new number which is called as Rayleigh number is simply Grashof number at x times Prandtl number. So, the turbulence in under these situations, the turbulence in natural convection is defined when Rayleigh number at the transition, which is Grashof number at the transition times Prandtl number, is about 10 to the power 9. So, this is the limit for Rayleigh number for the case of turbulent flow. The most common examples of natural convection is when you have a vertical plate and you have natural convection taking place from its sides. The most common correlation for finding out what would be the heat transfer coefficient under these conditions are given by Churchill and Cho, where the Nusselt number relation is provided as 0.825 plus 0.387 RAL to the power 1 by 6 and a complex function of Prandtl number see this is an impossible hopeless hopeless correlation to remember or to do anything with this. So, what the researchers have done over the years is they have a huge number of experimental data under various conditions, and they start with some heuristics, some logic that Nusselt number has to be a function of Grashof number and Prandtl number, or you can express it as Nusselt number has to be a function of Rayleigh number and Prandtl number. But the dependence on the Rayleigh number or the dependence on the Prandtl number, these are fitted, these are empirical expressions. Your theoretical analysis, your understanding would only tell you that Nusselt is going to be a function of Rayleigh number and Prandtl number. But how they are related, that is where the experimental data, the fitting etcetera comes in. So, there are several such relations available in the text. I am giving you some of the examples. Make sure you use the right correlation to find out the value of the heat transfer coefficient. All these correlations are valid for certain ranges of Rayleigh number. For example, turbulent flow and laminar flow, the crossover takes place for a Rayleigh number of about 10 to the power 9 and for certain ranges of Prandtl number. So, use those relations, but use them judiciously for the situation that you have at hand in order to obtain the value of H. But the important thing, one of the reassuring thing is that no matter which correlation that you use, the value of H is more or less it's insensitive to some extent to the correlation that you have used. So, the value of heat transfer coefficient in natural convection is very small. For the case of air, it is going to be of the order of between 1 to 10 watt per meter square per Kelvin. So, since the value of heat transfer coefficient is small and it does not vary too much based on which correlation you use, so your results are going to be approximately correct, no matter if you choose more or less a right correlation, and that is something which you have to keep in mind, but always consult your text or your handbook and choose the right relation for such cases. So, the relations that I have shown you so far are valid only when natural convection is predominant, but there would be situations in which both the natural convection and forced convection would be present. So, what would be the expression for such situations? I know separately how Nusselt number depends on Reynolds and Prandtl for the case of for the case of forced convection, and how Nusselt number depends on Rayleigh number and Prandtl number for the case of free convection. But if both are present and both are significant, how do I get the overall Nusselt number for such a situation? So, that is what I am going to write next. The case where both are important, that means you have the free and forced convection, both are important. Then the Nusselt number, the effective Nusselt number is Nusselt number based on pure forced convection plus or minus Nusselt number based on pure natural convection. So, this plus is for the assisting and transverse flow, whereas minus is for opposing flow. So, the Nusselt number for when both are present is simply an algebraic sum to the power some coefficient n, where this n is generally taken to be equal to 3. So, the value of n is generally taken to be equal to 3, and this is only a first approximation to find out what is the combined heat transfer coefficient when both are present. So, if you have both acting in the same direction, then it is going to be plus. If you have natural convection and forced convection are in the opposite direction, then you are going to have a negative sign. And the last one that you have is for uniform wall heat flux. This is another very common situation which you would obtain in the case of heat transfer in the case of natural convection, where the Nusselt number is denoted by a relation Grashof number x times Prandtl number to the power 1 by 5, and for some value of Grashof number Prandtl number within 10 to the power 5 and 10 to the power 11. So, and in for the case of turbulent flow, this is going to be 0.568 Grashof number x times Prandtl number to the power 0.22, where it is 2 into 10 to the power 13 Grashof number Prandtl number 10 to the power 16. So, this is for laminar, this is for turbulent. My idea is not to give you too many correlations, because these correlations are available in your text. You can look it up at any point of time. What I would like to take from this class is that I need to understand why the natural convection is taking place, and since it is taking place and there the pressure gradient for flow is provided by a difference in density caused by a difference in temperature. So, there would be an additional body force term, or the body force term will have to be modified by taking into account the difference in density. The difference in density is related to difference in temperature. So, it is more logical to bring in a thermodynamic quantity beta, which is the coefficient of volumetric expansion, and write the equation of motion in a clear fashion, which will highlight the role of temperature difference play in natural convective flow along, let us say, a flat plate. So, this additional contribution from the temperature gradient induced flow, the buoyancy difference induced flow, is clubbed in terms of a new dimensionless number, which is known as Grashof number. So, if it is purely natural convection, my Nusselt number correlation for various situations there will be different types of correlations, but Nusselt number would be a function of Grashof number and Prandtl number. If it is a forced convection only, then Nusselt number is a function of Reynolds number and Prandtl number. If both are present, then the effective Nusselt number is expressed as an algebraic sum of Nusselt number due to forced convection and Nusselt number due to free convection with an exponent n present in the relation. So, the values of n are generally taken to be equal to 3, and there are a multitude of relations which are available for Nusselt number under various conditions. So, the important thing to know here is that the value of the natural convective heat transfer coefficient is quite small as compared to their counterparts in forced convection. So, if you have a system in which forced convection is taking place inside a tube and free convection is taking place outside of the tube, the rate determining step, the maximum resistance to heat transfer is going to be provided by the natural convection, the natural convective heat transfer coefficient or the inverse of that, because inverse of heat transfer coefficient is the resistance to heat transfer. So, we have a forced convection heat transfer coefficient and a free convection heat transfer coefficient, and it is this free convection which would be the rate determining step in the overall heat transport process. So, an idea of the natural convective heat transfer coefficient is very important in many of the calculations that you would encounter while designing the heat exchange equipment. So, identifying the flow pattern, identifying the role of natural convection in that process vis-a-vis forced convection, and choosing the right correlation for that specific situation are all very important. The first two I have covered extensively in this class, but the choosing the relation or which relation to be used and what would be the form of that, they are available in the text. So, I would encourage you to look at the text and see for what condition what correlation is to be used. So, that is in a nutshell what natural convection is all about. The values for the convective heat transfer coefficient are between 1 to 10 watt per meter square Kelvin for natural convection in air, and there are if you compare that with forced convection, they are quite low, and they are, since they are small, they offer the maximum resistance to heat transfer. So, that is all for natural convection, and in the next class we will start the actual what an heat exchanger would look like, the types of heat exchanger, the calculations involved, and so on.